Okay, today we're going to talk about something with just 3 letters in it, KMT, but that's really short for kinetic molecular theory. Okay, so let me tell you a little bit about what kinetic molecular theory is. If you remember a little bit earlier, hopefully you watched these videos on the empirical gas laws. And the empirical gas laws provided relationships between pressure, volume, temperature, but these people that came up with these equations had no idea why they worked. They just sort of worked, right? And so they came up with formulas that related pressure and volume, or volume and temperature, or volume and number of moles, or pressure and temperature. But they didn't really have a theoretical understanding for why things seemed to be the way that they were. So that's where this kinetic molecular theory comes in. Kinetic molecular theory provides an explanation for the behavior of gases. Okay, but one thing I do want to point out is it's just a model, which means that it's not exactly a perfect description of reality. It's meant to give you just kind of an idea of what should be happening. It's a simplified version of reality. But the vast majority of the time, it works pretty well. And if it doesn't, we'll fix it. And I'll show you later how things that deviate from kinetic molecular theory can also be accounted for. Okay, so now let me tell you some of the postulates, or the underlying kind of premises of this kinetic molecular theory. Okay, the first one is that a gas is made out of little particles, which we can think of as being molecules or atoms that are perfectly spherical. Okay, and so right off the bat, I know this is wrong, okay, because molecules do have certain well-defined three-dimensional shapes, right? They can be tetrahedral, or trigonal planar, or linear, but we're going to keep it simple and assume that everything is a perfect sphere. Okay, now these particles are always moving around, okay, so they're going to be constantly, randomly moving in every possible direction. Okay, when they move, we're going to assume that they move in straight lines, which basically says that they don't accelerate. Okay, they have a constant velocity. And as they're moving, these particles are going to be super, super, super far apart from each other, which is basically a nice way of saying that a lot of the container is going to be empty space. If I look at the volume of the container, right, how big the thing is compared to the volumes of the isolated individual gas molecules, the volumes of the molecules are really, really, really small compared to the volume of the container. Okay, so that takes care of volume. Another thing that we cared about was temperature. Okay, and so we're going to propose or postulate that the temperature is going to be proportional to the average kinetic energy of the motion. Okay, kinetic energy from physics land has to do with how fast things are moving. And you can think of how fast things are moving as being related to how much energy they have, right? If I have a lot of energy, I'm doing this, okay? And so if I have a lot of kinetic energy and I'm moving around a lot, that probably means that I can move around more, and we're going to associate that with a higher temperature, okay? So the higher the average kinetic energy, the higher the temperature, okay? And so that takes into account 2 of my 3 variables, right? I have a pressure and a volume and a temperature in my ideal gas law. This so far accounts for volume and temperature. Now I have to deal with pressure, okay? And so let's do that next. Here's the thing with pressure, okay? These particles are moving around a lot in the container, okay? And eventually, as they're moving, one of 2 things is going to happen, okay? Either they hit each other. Imagine 2 particles just doing this, okay? And if they collide, we're going to assume that these collisions are perfectly elastic, which basically means think of them as billiard balls, right? They hit, and then they just bounce off, go in the opposite direction, but there's no real change in their speed, okay? Velocity is the same magnitude, but opposite direction. So they can hit each other. Another possibility is they hit the walls of the container, okay? If they hit the wall of the container's not going to go anywhere, right? It's rigid, it's fixed, but the particles can bounce off, okay? And so every time that they bounce off the container, we're going to think of this as a pressure, okay? And so you can think of pressure as how many collisions there are with the walls of the container. Okay, so now we've taken into account pressure, volume, and temperature. Okay, that's the essence of the kinetic molecular theory. We have equations or models to describe behavior for these 3 variables, right? Pressure, volume, and temperature. Biggest drawback is we're assuming certain things, like the particles are perfect spheres. And another drawback that I didn't mention that I'll tell you now is we're assuming that there are absolutely 0 forces of attraction or repulsion between these particles, which basically means that there are no intermolecular forces, right? Each particle is doing its own thing, and when they're moving randomly, they don't care where anybody else is, okay? Every motion is independent of every other motion. In truth, that's not exactly right. There's a little bit of attraction or repulsion between them, which messes things up a little bit, but for the most part, for most of these gases, we can ignore those effects and still use the kinetic molecular theory the vast majority of the time.